Hello all, welcome back to the Algorithms and Me. Let's discuss another problem today. This problem is very simple, but it is commonly asked in interviews. And the problem goes like this. Given an integer array and an integer k, we have to find if there is a pair in this array which add up to the k. For example, let's say we have been given an array which is 3, 4, 5, 2, 6, 8, and let's say we have been given k equals to 10. We have to find out whether there are two numbers which add up to 10. In this example, there are two pairs such that which are adding up to k, which is 10. In this case, 4 plus 6, this and this are adding up to 10, and this is adding up to 10. So in this case, we will be returning any of these pairs and we'll have our answer. So let's start with the solution. How can we do that? One of the first thing which comes to our mind is a brute force solution. The brute force solution would be, I take this number and I search in the remaining array if I find k minus this number, right? If I find k minus this number, then that number and my current number can add up to the k, right? So what I'll do is I will write a quick two loops. Like I will go, hey, integer I equals to 0 and I less than n, where n is the size of my array which is given, and then I will do like, hey, for j equals to, it will be integer j equals to I plus 1, so I search on remaining array, and j also is less than n and j plus plus, and I just check if a of I plus a of j equals to k. If yes, all I need to do is return this pair. We can define which data structure we want to return it in, as a pair or as a list or as a set, whatever we want, but just return it from here, right? Else we'll go to the next j till the time we run out of j's, and then we go to the next I. The complexity of this code is very easy to calculate. This loop will run O of n, right? And for each I, this loop will run for I minus 1 plus n minus 2 plus n minus 3, all the way to only once. So overall, we'll be running this operation for O of n plus 1 divided by 2, which is nothing but O of n square in worst case. How can we reduce the complexity of this algorithm then? If we'll let me clear in the screen first so that I can explain it better. Okay, this is the loop where we are searching for a corresponding j which matches with I. Can we reduce the complexity of this particular piece of code from O of n to O of 1 and then reduce the complexity of our solution? How about we use a hash map to store all the j's which are there, right? So what we can do is we can go through the array first and create a hash map of all the numbers. Then we go from the array again, and for each number we search into the map whether there is a complementary number. The complementary number is the number which when added to the current number gives us k, right? We do that for each number. So this search function reduces to O of n, and even though we do an extra traversal of the array, which we can actually optimize, when I write the code I'll show you, right? But we reduce the complexity from O of n square to O of n. However, we increased our space complexity from O of 1 in the earlier solution to O of n in this solution. So let's quickly write the code for this solution. So the code will be something like this. There will be a map which will store the number and its corresponding index. Let's call it map and we'll declare it new hash map. And what we'll do is we'll go through each one of the integer. So for integer I equals to 0, I less than n, I plus plus. And what we'll do is we'll check if the map contains the complementary number, right? So what we'll do is if map dot contains key, and what should it contain? It should contain k minus the current number, right? That will be the complementary number. If it contains that, right, that means we have to return the current number, which is I, and map dot get k minus a of I, which is the complementary number index. Great. If it is not there, all we have to do is we'll just add this number to the map, and this is where we save the first scan. We don't have to actually add them beforehand. We can add when we are processing. So we'll just do a of I and we'll introduce the complexity of this code is now reduced to O of n with the space complexity because of the map, which is O of n. Now, what if I told you not to use any additional space, right? So we saw a solution which is O of n square. We reduce it to O of n, right? But we increase the space complexity from O of 1 to O of n. If we want to reduce the space complexity, that means we want to go this way, right? And we don't want to end up at O of n square. That means we have to find a solution which works in n log n, right? And if you hear n log n, right, in any of your solution, think sorting. Can you do anything by sorting this array beforehand, right? Let's try that. Let's try this on this input. So our input was 3, 4, 5, 2, 6, 8. So if I sort it down, it will become 2, 3, 4, 5, 6, and 8. Great. What if I use two indexes? Let's say I and j. So I points to the starting index and j points to the last index. What if a of I plus a of j is equals to k? In that case, I found the pair. Found the pair, right? What if a of I plus a of j is less than k? That means the sum of these two numbers is less than k. I need to increase the sum, right? In that case, what will happen? I have to increase the I. Why? Because that will add, because the array is sorted, that will add more value to the sum. I cannot decrease the j because that will reduce the sum, right? So I'll do I plus plus. Now, if a of I plus a of j is greater than k, in this case I have to decrease the sum. So I will move the j left. That will decrease the overall sum and that will increase the possibility of me finding the pair which add up to a particular k. So in this case I will do this. How long will I do? Till I and j cross each other or equals to each other, because we cannot have like same number adding up to, like if we meet at 5, we cannot have 5 plus 5 because I and j are both on a 5. So even if the I and j are equal, then we should stop. We should not wait for them to cross each other. Great. Let's quickly write the code. code would be something like this. We have been given an array, so the first thing we'll do is we'll sort the array A. Great. Now we have sorted this array. What we have to do is we have to define two indexes, I equals to 0 and integer j equals to a dot length minus 1. Right, this is an index, not the length, so minus 1. Now what we'll do, while I is less than j, remember this is not equals to, it is less than j, because if they become equals to, there is only one element and we don't want one element, right? We want a pair. What we'll do, if a of I plus a of j is equals to k, we just return I comma j. If a of I plus a of j is less than k, in that case we have to increment, right? So we will increment the I, else we will do j minus minus. The complexity of this solution is O of n, and we are not using any additional space, but that's the big mistake everybody makes, or most of us make in an interview. We forgot to include the complexity of the sorting algorithm in this, right? Which is in best case n log n, right? Actually, this sorting algorithm complexity dominates the complexity of this solution. Hence, the complexity of the overall solution is O of n log n. So we solved the problem in 3 different ways. We saw the dance of complexities around each of the solutions. If you have any doubt, any comment, any suggestions, please drop it in comments. Thank you very much.